So now that we've seen a general introduction to how these reactions are written, let's look at some of the reactions that we're going to see in the upcoming chapters. So one of the reactions that we're going to see is a substitution reaction. In this type of reaction, what happens is literally that one compound, like this one that has a Z, that Z is a leaving group, right? So, and as the name says, that leaving group will leave, and then the Y will come in and substitute the Z, right? So the overall change that you're going to see is that the Z is going to go and the Y is going to come in. So in this type of reactions, one bond will break and then a new bond will form right there. So in this type of reactions, what happens is that it involves two bonds. So one of the sigma bonds will break and one of the sigma bonds will form, right? So in this case, you see we have the Cl minus, remember, that is going to be our nucleophile. So that nucleophile can come right here, and because that carbon is already connected to 4 things at a time, then that iodine will leave. And so now this iodine is here, right? Our leaving group just left, and now the nucleophile is connected to the carbon. So something similar happens in this reaction too. So the bond that is going to break is this one, because the Cl will be my leaving group at this point, and then my nucleophile is going to be the O minus, right? So remember that oxygen has 3 lone pairs, so it can come and attack there on the electrophile. Remember that that part of the carbonyl is electrophilic, because the oxygen is pulling away electrons from that center. So then the oxygen comes, attacks, and pushes up the electrons. And so then at that point, what will happen is that we will have that, right? So we still have the Cl connected, and then at that point we have the OH connected right in there. And so when these electrons come back down, that it's the weaker bond, you see that CCl bond is the weaker one because the Cl is very electronegative, so that's the weaker bond. So then that will break and that will give us the final carboxylic acid, right? So we are going from an acyl chloride into a carboxylic acid. You recognize the functional groups, right? So this reaction happened in one step, the top one, and this reaction happened in 2 steps. The first step where the nucleophile attacked, and then the second step where the leaving group left. So yeah, these reactions, so these happen in 1 step, these happen in 2 steps. So we will call this molecule right here, right? That is an intermediate. Right? So that's our intermediate right there, because the reaction doesn't go straight from A into B, the reaction goes from A to B to C. You see that? So instead of doing that, we go from A to B to C. Okay? So in some cases, Z, in very specific cases, this C right here could be a hydrogen. But in most of the cases, that C is a heteroatom, more electronegative than carbon. And I want you to pause the video here and think why that may be. So why do you think these type of reactions, these substitution reactions, happen when you have a leaving group, a Z, that it's an atom that it's more electronegative than carbon? Pause the video here and try to figure it out. So the reason for that to happen is because the Z, when you have a carbon connected to a hydrogen, that bond is harder to break than if you have a carbon that is connected to a chlorine. Do you remember why? The reason is because chlorine is pulling away electrons, it's polarizing this bond, and therefore it's easier to break. Carbon and hydrogen, these electrons right here are tightly connected together. So that's why this bond will be harder to break than this one. And then another type of reaction that we will see is an elimination. So an elimination reaction, basically what happens is that you will eliminate two groups, the X and the Y. And in elimination reactions, you always get a pi bond form. So that means a double bond or a triple bond. And so in this case, two sigma bonds will be broken and one pi bond will be formed. Okay, and my side compound will be the XY right there. Okay, so these two will connect together right here. So again, two groups will leave the main molecule. I will end up with a double bond, and my side product will be those two groups being together. So these are some examples of elimination reactions. So what will happen here is that the H and the Br will leave, and so I will end up with a double bond right there. And so, you know, the living groups end up here. They don't always have to end up together. It's common, just like here. They don't always have to end up together, but you'll see cases. You will see both cases. And so another example is here where we lose, formally we lose a molecule of water, right? Because we lose the H and the OH here, that when they connect together, you end up with water right there. And so you form a new pi bond. So the opposite of that reaction, it's an addition reaction. And what you do is that you start with a double bond, and then you will add an X and you will add a Y across the double bond. So it's the opposite from the previous one, because in the previous one you started with two pi bonds that were being broken, end up with not two pi bonds, two sigma bonds being broken, and you will end up with a pi bond, you will end up with a double bond. In this case, it's the opposite. You start with a pi bond, and then you end up with two sigma bonds being formed. So those two reactions are opposite. So let's look at two examples of addition reactions. They are the same example that we saw before. So before we were here, and then we end up with a double bond, and now we have the double bond, and so you see how the H connects there and the Br connects there. We will explore how these reactions happen stepwise, right? It's not as simple as simply connect them right there. And then here we have this double bond, same thing. Formally, we end up with the H there and the OH right there. And so, as I mentioned before, these reactions are opposite. So in the elimination reactions, a pi bond is formed, and in the a sigma bond is broken. Where's the here a sigma bond is broken in addition reactions, right? So in elimination reactions, here we will form the double bond, and in addition reactions we will break that double bond.